Thomas Barends from the Max Planck Institute for Medical Research at Heidelberg, Germany. And the title of his lecture is Watching Molecules at Work with Free Electron Lasers.
Firstly, let me introduce Thomas. So Thomas studied chemistry at Groningen University in Netherlands, where he also obtained his PhD degree in protein crystallography in a group of Professor Bauk Dijkstra. He then moved to Department of Biological Mechanism at the Max Planck Institute in Heidelberg and did a postdoc with Professor Ilme Schlichting. He has been at the MPI since then, firstly as a staff scientist, and now he's an independent group leader, investigating molecular mechanism of anaerobic ammonium oxidation and helping to develop methods for structural biology using free electron lasers. Thomas has published impressive, almost infinite numbers of papers in Nature and Science. Thomas, the screen is yours.
So thank you very much for allowing me to present our work here. So like we said, it's called Watching Molecules at Work with Free Electron Lasers. And so my institute was heavily involved in the Department of Biomolecular Mechanisms, but as you will see, these are very, very large collaborations. We are protein crystallographers. Mainly, we do protein crystallography, and protein crystallography is a very, very successful technique, but there are a couple of things that I would like to be able to improve about protein crystallography. And one of those things is that I'd like to be able to do it in a very, very fast, time-resolved manner. If you look at this time scale picture that I have drawn here, one generation time of an E. coli cell is about 20 minutes or so. That is about the time scale also of a protein crystallography experiment. But of course, what we are interested in is enzyme catalysis, and also what is behind things like enzyme catalysis and all kinds of biological processes. Side chains that are changing position, that are rotating, bonds that are vibrating, and those processes happen on timescales of picoseconds to nanoseconds. And we'd like to be able to study those, and I'd like to be able to do that with crystallography. Now, to see a side chain move, we would need to be able to do protein crystallography with a time resolution better than a picosecond. So that's one thing that we'd like to be able to improve about protein crystallography. The other thing is something that is often conveniently forgotten by protein crystallographers, at least. If you put a protein crystal in an X-ray beam, almost all of the photons go straight through and they don't interact with the sample at all. And of, say, 10 photons that do interact with your protein crystal, only one of them, only about 10%, actually contributes to the Rayleigh scattering that gives us our diffraction pattern. The rest does either Compton scattering or engages in photoelectric effect. And so those types of interactions, so for instance, photoelectric effect knocks out an inner shell electron, and then depending on the Z number of your element, you either emit another electron, an Auger electron, a little bit later, or you do fluorescence. In any event, you're generating a large number of electrons, and they're going to move through your protein crystal, and they're going to do an enormous amount of damage. And this is something that is often conveniently forgotten by protein crystallographers, but which is a huge problem when it comes to, for instance, enzymology of metalloproteins. So that is also something that I'd like to be able to improve about protein crystallography. And with these free electron lasers, both these things, both those improvements can now be made. So what is a free electron laser? It's a very, very special X-ray source. The one that's shown over here, I got this picture from the LINA coherent light source at the Stanford Linear Accelerator Center. This is a former electron accelerator for particle physics. And what they've done, they've left a large part of the accelerator intact, so they accelerate electrons here, and then the electrons go into a very, very long undulator, much, much longer than the ones we are used to at synchrotrons. And what happens is you get sort of a lasing effect, and here in the experimental holes you then have X-ray pulses, which are extremely bright and which are also extremely short. And if you compare the peak brilliance of free electron lasers with those of synchrotrons, for instance, you compare, for instance, the LCLS with Petra 3, then you see you have an increase in peak brilliance of up to 9 orders of magnitude. And what is more, the pulses that you get from these free electron lasers are extremely short. They can be tuned between 3 and a few hundred femtoseconds. And you get about 120 pulses of these every second, at least at the LCLS. But this is now also increasing into the megahertz range. Like a synchrotron, they are tunable, and it's also transversely a fully coherent radiation. So and with these very, very short pulses, you can then do very, very high time resolution studies also on protein crystals. Moreover, because the pulses are so short, you will still get photoelectric effect. You will still generate photoelectrons, but because the entire pulse lasts only a few femtoseconds, the atoms simply have no time to move during such a brief pulse. So yes, there will be damage. In the end, the sample will evaporate. It will explode in what is called a Coulomb explosion. But during the pulse, because of simple inertia, the atoms simply have no time to move. So the structure that you're looking at in terms of atomic positions will be almost entirely unaffected by radiation damage. So with these free electron lasers, we can make those two improvements that I desired. You can do very, very high time resolution, and you can maybe look at proteins without a lot of radiation damage. So those are the two things that I'd like to show today. And so let's start with the high time resolution. One of the things we're very, very interested in is doing time-resolved pump probe experiments on photosensitive proteins. And people have done this before at synchrotrons, and arguably the best time-resolved protein crystallography study ever was done by Friedrich Schotte and Philip Anfinroot, and it had a time resolution of about 100 picoseconds. But with these free electron lasers, we can maybe reduce this to picoseconds, or maybe even less than a picosecond, maybe hundreds of femtoseconds. So how could you do such an experiment? Well, you would have your free electron laser beam. It's not really a continuous beam. These are pulses, and you have to get a crystal into that beam in some way. And the crystals that we use for these experiments are very, very small. They're maybe just a few micrometers in size, but that is enough with such a high peak brilliance. But because every crystal is immediately destroyed by the X-ray pulse, you need to replenish the crystal. For every diffraction pattern, you need a new crystal. So what is done in practice is you use, for instance, a liquid jet. That's an apparatus that makes a very, very thin stream of liquid, maybe 1 to 2 microns in diameter. And through this, you pump a suspension of microcrystals. And this jet intersects with the X-ray beam, and then you get diffraction patterns on a detector behind the interaction region. And now you will see that there is something missing that you have in every classical crystallography setup. What is not drawn here in this picture is a beam stop, because a beam stop would actually also evaporate. It would at least heat up enormously. So what is done in practice is that you leave a hole in the detector that the direct beam goes straight through, and then you have a system for dealing with that behind the detector. So this setup, that would be the setup for data collection, protein crystallography data collection with a free electron laser. And now what we want to do is go one step further. We want to trigger a reaction in our protein crystals. We want to do this with a pump laser, so with a visible light laser. So we have a crystal arriving in the interaction region. We start a reaction in that crystal with a visible light pulse, and then a few hundred femtoseconds, a few picoseconds or nanoseconds after that, the X-ray pulse arrives and you probe what has happened in the crystal. So we're doing pump probe experiments, and we are starting the reaction with a visible light pulse, that's our pump, and then we probe the structural changes in the crystal with our free electron laser pulse. And so the model system that we chose for this is myoglobin. Everybody knows myoglobin who has ever eaten a steak. Myoglobin is an 18 kilodalton heme protein, and it stores oxygen in muscle tissue. And it has this heme group over here, and the oxygen binds to the iron in the heme. But this was actually the first protein structure that was ever solved by crystallography. And you don't see it very well in this, or you don't see it at all in this representation. But when that structure was solved, the people who did it immediately realized that there is more to the story than just a static structure, because there is actually no opening for the gas molecule, the oxygen molecule, to get into or out of the protein. So already from the very, very first protein crystal structure that was ever solved, it was already clear that there should be structural changes to allow this protein to function. And it is those structural changes that we want to probe with our experiment. Yeah. Now, luckily for us, myoglobin does not only bind oxygen, but it also binds carbon monoxide in exactly the same way. It binds to the iron of the heme, and you can break the heme CO bonds with visible light. Yeah? And the reaction of the protein to the release of the ligand has been studied by every method under the sun. This protein is a paradigm for the study of protein dynamics, and this is the protein to do that with. And from all those studies, we already know what's going to happen. Yeah, people have done static crystallography as a structure with and without CO. People have done time-resolved crystallography. That was, for instance, the study by Schotte and Untitled that I talked about. People have done spectroscopy of all kinds. People have done simulations. So we know what is going to happen. Upon absorbing a photon, this CO molecule is going to leave its binding position. It's going to move to a pocket somewhere over here. And that happens in 100 femtoseconds. It's extremely fast. And then the protein starts to react. This helix over here, the E helix, it moves in that direction. This helix, the F helix, moves in that direction. This helix follows the E helix. This loop moves there. We basically know what is going to happen. Yeah? And the effects of breaking that bond, they spread out over the protein like an earthquake. And if you, then Hans Frauenfelder has done that. If you know the speed of sound in a protein, then you can predict that those effects will reach the outside of the molecule in 2 to 3 picoseconds. Hans Frauenfelder called it the protein quake. Yeah, but previously, the very best structural data had a time resolution of 100 to 150 picoseconds. Yeah, so you could sort of see what had happened. You had again a before and after picture, but you could not actually follow the changes as they happened. But with the free electron laser, you can actually do that. You can see those motions happen. So what is the experiment that we actually did? We made microcrystals, just 1 to 2 microns in size, of horse-heart myoglobin. And this is what the suspension of horse-heart myoglobin crystals looks like. It's this brown suspension. And then if you incubate this with carbon monoxide, it changes color and you get this beautiful raspberry red suspension of crystals. We inject those with a liquid jet. We hit them with an optical pump laser, 532 nanometers femtosecond laser, and then a few hundred femtoseconds to a few picoseconds after that, we probe the crystal with a free electron laser pulse. And we have done this at various time delays, varying from 100 femtoseconds to 150 picoseconds. And of course, we also collected a lot of data where we had the pump laser switched off so that we could compare the dark state of the crystals with the light-triggered state of the crystals. And so if you then look at electron density maps in, for instance, the binding site on the heme, you can calculate different electron density maps, like, for instance, this one over here. This is at a time delay of 10 picoseconds. So that is 10 picoseconds after starting the reaction. You have the heme over here, and you see negative difference electron density in red over here, where the carbon monoxide molecule was. And here, a very, very large positive difference electron density peak. So the CO has moved from here to here. This histidine residue over here has apparently rotated into the gap left by the CO. And you also see that the iron of the heme has rebounded. That's also something that was expected from spectroscopy and static studies, and that it's actually pushing this histidine down here. So that is 10 picoseconds after the light trigger. So that's already an order of magnitude higher time resolution than was possible with previous studies. If you now rotate this picture by 90 degrees and you look on top of the heme, then you see again here this difference electron density of the carbon monoxide changing position. But you see, for instance, this phenylalanine over here seems to have shifted a little bit in that direction at 10 picoseconds. But we have many, many more time points. For instance, at 0.5 picoseconds, 500 femtoseconds, it seems to have shifted in the other direction. And so we have many, many time points like this. And so now you can actually make a movie. And for instance, well, I haven't drawn the CO here, it's moved from here to there, but you can actually see how this histidine rotates into the void left by the carbon monoxide, and how the histidine, this other histidine, the proximal histidine it's called, is pushed down by the iron. Yeah? So the changes that you are getting are relatively small, but we do not only see changes in side chains, we also, you can already see it a little bit over here, you see these helices move here. So now we have this really, really high time resolution movie of what's happening in myoglobin when you lyse this iron CO bond. So we see large scale changes over time. I have plotted here on the structure the displacement of the C alpha atoms with respect to the center of the heme. And you see exactly what we expected. This E helix here moves towards the heme, this F helix moves away from the heme. And you also see that this is something that starts very, very quickly, but that motion increases in amplitude over 150 picoseconds at least. So we see very, very large scale changes over time. But we also see very, very fast motions of individual amino acids. Here, for instance, this is this phenylalanine that we showed earlier. This is the chi-1 angle, and it seems to really change its chi-1 angle. So that's the rotation about the C alpha C beta atom very, very quickly. The same holds for this valine, and this isoleucine reacts a little bit more slowly. Those are residues that from molecular dynamics you would expect to be hit by the CO as it moves into its new binding pocket. So that is entirely consistent with predictions. But these residues over here, so this, for instance, is the length of a hydrogen bond, they seem to oscillate. Also this histidine 93 chi-1 angle, and also this hydrogen bond distance between this lysine main chain O and this side chain N. And the period of that oscillation is around 400 femtoseconds. And that we found very, very interesting, because we know from spectroscopy that the heme in myoglobin has a doming mode, as it's called, which has a period of about 400 femtoseconds. So it looks as though we can actually see those vibrations and oscillations that we know from spectroscopy. And all of this fits really nicely with a model for myoglobin dynamics in terms of normal modes of the protein. And the motions that we see are actually comparable to one of the normal modes of myoglobin. So that was a really, really nice, successful story. And now, of course, we can do this with other systems as well. And so we have looked, for instance, at bacteriorhodopsin And bacteriorhodopsin is this light-driven proton pump in the membrane of some bacteria. It has this retinol chromophore, which absorbs light, and then there is a cis-trans isomerization around this bond here. And that, again, affects the local structure of the protein, and it results in proton translocation. And like myoglobin, it has been studied with a large variety of methods. And so we've done this same experiment, just with a different protein and slightly different laser wavelength. And you see here, for instance, the changes in that chromophore at 3 picoseconds and at 10 picoseconds. And again, what we see, we have this network of active site residues. And again, we see these coherent motions, these oscillations, all with similar frequencies. And so what we are now doing is looking at how these oscillations, how they correspond to the function of the protein. But yeah, we should be a little bit careful. This is part of the abstract of the paper we wrote about this. Yeah, here we use time-resolved crystallography, blah blah blah, to follow the structural changes. So far, so good. In multiphoton excited bacteriorhodopsin. We specifically say multiphoton excited bacteriorhodopsin. This is a really important point that we're trying to make here. Because this multiphoton thing could be a real complication. Yeah? Protein crystals have really, really high protein concentrations, up to several millimolar. And so chromophore absorption is going to be very, very high. Now, to get a reasonable fraction of molecules excited in your crystal, you're going to need many, many photons. And to do this with high time resolution, you would need to pack those photons into a very, very short pulse of just a few femtoseconds. And together, that leads to an enormously high pump laser power density. Several pump probe studies of the sort that I've just talked about, also our own, used up to 500 gigawatts per square centimeter. If there are any spectroscopists in the audience, they will now be rolling on the floor laughing. Nobody in their right mind would use a power density like that. It corresponds to 10 to 100 photons per chromophore. Yeah? And so I am afraid that there is a really good chance that you will get multiphoton absorption and nonlinear effects. And of course, that is not something that is going to happen in nature. Yeah? So we should be really, really careful in interpreting these results and make sure that we're not looking at some artifact of multiphoton absorption. And so Marie Grunbein, a PhD student in our department, she's looked into all of this and has come up with some illumination guidelines for these ultra-fast pump probe experiments. Indeed, Dwayne Miller, he published this. He commented on this. There are many, many different pathways in which a multiphoton state could go back to the ground state, and they're probably not all physiologically relevant. So what should we do? We should repeat all our experiments in the one photon regime and repeat all of this, making sure that we're absorbing at most 1 photon per chromophore. So far, we've done that for myoglobin, and we've looked again at, for instance, these histidines on top of and below the heme here, and we see those same oscillations. Yeah, so we can get that result back. That was not a multiphoton effect. The same holds actually for this phenylalanine that I've shown before. You see here, this oscillation here seems to actually increase in amplitude. These data were measured at Swissfel. It's another free-electron laser, and it's really, really nice data. And we still get those 400 femtosecond period oscillations. But in other respects, the data are very different from our original data. For instance, we seem to get an increase of the photolyzed CO occupancy with increasing pump probe time delay. Yeah? There seems to be a time constant of, say, 300, 200, 300 femtoseconds or so. And well, we collaborate with quantum chemists, and one of the things that they see when they simulate this process is, well, if you look at the iron CO distance, that actually at early time delays oscillates very, very strongly. And this, of course, would smear out our electron density, and we would get an apparent occupancy that is only partial. Yeah. So right now we're thinking that this could actually explain this observation, but it's an observation we did not make in the multiphoton regime. So our results, they differ significantly between single and multiphoton excitation. So you have to be a little bit careful with this multiphoton effects. Yeah. But still, it works. With these free electron lasers, you can really do extremely high time resolution dynamic studies in the crystal. So that is one thing that I wanted to do. The other thing that we wanted to do was get around this radiation damage problem. Yeah? Like I said, 9 out of 10 X-ray photons that interact with your crystal, they don't do useful scattering, they do damage. Yeah? And the sort of worst case protein for radiation damage caused by X-rays is photosystem 2. That's part of the green stuff in plants. And it has this very, very intricate cluster made up of oxygen atoms, manganese atoms, and calcium atoms. And the people who study this, they know that when you put this stuff in an X-ray beam, the damage done to this cluster is basically instantaneous. Yeah? And so there are many groups. We don't work on this, but there are many groups that are working on this that are now using free electron lasers to get around this radiation damage problem. And the way they do that is by making use of these extremely short pulses. If you use pulses of only a few femtoseconds, then the atoms simply have no time to move, even if they are ionized. Yeah? You would still get the same structure. Yeah? So, and I think the most impressive study of photosystem 2 was done by Suga and co-workers at the Sakura free electron laser in Japan. And they didn't use a liquid jet. They made very, very large crystals and cryo-cooled them in loops, as protein crystallographers always do. And then they just shot it at different positions. They could rotate their crystal, and in that way collected fresh parts of the crystal, just one shot per part of the crystal. And they got really, really impressive results, very, very high resolution. And indeed, they see differences in the structure of this metal cluster between their X-FEL-derived structure and this classical structure. And with that, they could now propose a mechanism for how this photosystem works that is unaffected by damaged structures. So I thought that was really, really impressive. Another example of mitigating radiation damage, Tosha and co-workers, they looked at P450 NOR, that is an enzyme. It also has a heme group. And if you bind nitric oxide to the heme group and determine the structure, then you will see that there is an angle between this angle between the oxygen, nitrogen, and iron atom. And the value of this angle depends very, very much on the electronic structure of this thing. So it is really, really relevant. But yeah, it's also really, really radiation sensitive. If you do a low dose synchrotron experiment, you get an angle of about 147 degrees. But if you just keep your crystal in the beam and keep collecting, that angle decreases to 122 degrees. So there is radiation damage going on, and it is likely that these data are already affected by radiation damage. So what they did is they determined this structure again, but now using an X-ray free electron laser, and they found a much, much larger angle of 158 degrees. And if you then compare where that angle is, the X-FEL result with predictions from QMMM in various ways, then you see it fits extremely well with what is predicted for this angle from quantum chemistry. And I think that is a really, really impressive result. Yeah. Again, let me introduce a word of caution. Yeah. Many of those XFEL talks, also the ones that I give, they are a bit like they're the greatest showman. Yeah, like it's all fantastic and XFEL solve all your problems, and who needs EM and actually who needs synchrotrons? Is there really never any radiation damage when you're using an XFEL? So that's where we've been doing some experiments. We've looked at various systems, for instance, lysozyme with very, very heavy atom labels. But we've also looked at this ferredoxin. It's a very, very small protein, and it has 2 iron-sulfur clusters. And iron-sulfur clusters are, of course, magnets for radiation damage. They absorb a lot of X-rays and can generate a lot of photoelectrons. And this protein gives really, really well diffracting crystals. So we put this in an XFEL beam at very high fluence, and we did that above and below the K absorption edge of iron. And then we compared our data with very, very low dose synchrotron results. And this is something that was done by Karel Nas. And so what you see here, if you use a really, really high dose, also at a free electron laser, you see actually the electron density map over here clearly shows that these sulfur atoms are flying away. Yeah? So this thing is actually undergoing what we call a local Coulomb explosion, and it has become ionized so much that that after 80 femtoseconds, it's actually starting to fly apart. Yeah. And simulations by Stefan Haurige and his co-workers, they predict exactly this effect. And you see also that the sulfur atoms, they fly further simply because they are lighter. Yeah. So if you use too high a dose, then you will also, and very, very long pulses, you can actually also get radiation damage, and rather impressive radiation damage at that, if you use a free electron laser. Yeah. Interestingly, and this might interest the quantum crystallographers, it's not only the iron-sulfur clusters. If you use a very, very high fluence, and this is just tomatin and lysozyme, yeah? I'm showing here the blue mesh is a 2FO minus FC, sigma A weighted 2FO minus FC electron density map. But in red and green, I show at 3 sigma the difference electron density between, before and after, between the first and the second X-ray pulse. And you actually get deviations from the expected electron density. What I did here is that I just averaged the electron density for every little peptide in the protein. And then this effect actually comes out. It seems that electrons are depleted here and they're moving there and there. But then there also seems to be some equilibration. This is as close as I have ever gotten to showing deformation density type things. But this is from proteins in an XFEL beam. So I don't know what the mechanism behind this is. I just think we should be careful, and also with free electron laser beams, think about what you're doing. Don't use brilliance that is too high or pulses that are too long. Now, our latest experiments, and this is again with this ferredoxin. Here I have symmetry averaged every orientation of the two things, and then you get a really, really nice effect. Even at shorter pulses, there are indications of local radiation damage to electron-rich clusters in proteins. So we think we need more research to determine what can and cannot be done in terms of experimental design of these experiments. How long can my pulses really be? And how high can my intensities really be? But other than that, XFELs, they allow time-resolved structure determinations, and they also allow you to simply outrun a lot of radiation damage. Yeah? Still, if you use too high intensity and pulses that are too long, you can still get radiation damage, so care is needed. And also when you do these light triggering pump probe experiments, you need to be very, very careful about how many photons you actually pump into that thing. but we are looking at what effects are at play and developing data collection strategies to use or to avoid. Yeah. Now, these experiments, they're done by a very, very large number of people. Our department is the Department of Ilmenschlichting at the MPI for Medical Research. But of course, the beamline scientists, the accelerator scientists, the technicians at the Free-Electron Lasers, also the quantum chemists that we collaborate with, the spectroscopists that we collaborate with. And this is just acknowledgement slide 1 of 2. This is just for the ultrafast protein dynamics. For the ultrafast radiation damage, it is the same story. And the last thing I want to show is this picture. In this picture, it looks as though I am the boss or something. And the only reason that I'm in the middle here is that I was late for taking the picture. All of this work is led by Ilmenschlichting, who is our departmental director. And you see here just a few people from the LCLS and from our department who do all the work. Thank you very much for your attention.
Thank you very much, Thomas, for this really brilliant, excellent lecture, which is now open for questions and comments. And before they appear in print on our chat, could I ask my question? How do you obtain those electron density maps? Are they obtained using just routine X-ray refinement based on independent atom model based on atoms?
It is as soon as the data collection is a little bit different, or the data processing is a little bit different. I haven't gone into that right now, but you cannot rotate a crystal during a 10 femtosecond pulse. So what you have is still images. You get a lot of partial reflections, and you don't get as many reflections on each image, depending on the mosaicity. So the group in Berkeley, Nicholas Sauter's group, have developed software to deal with that. Wolfgang Kapsch at our institute has developed software to deal with that. And Tom White's CFEL in Hamburg, and that's the software that I use the most, CrystFEL. And that deals with that is capable of indexing and integrating those reflections. But once that is done, it turns into completely normal protein crystallography. And so you use CCP4 and Phoenix and all the standard programs. That is not to say that I don't write my own software to do these weird averaging things and to calculate maps for the time resolved stuff. Of course, but in principle, this is completely normal protein crystallography. So terrible intensities saved by really good phases from a model.
So next question. What is, I would say, routine resolution of your data you are obtaining this kind of experiment?
Yeah, we carefully choose our model systems. So we did this first phasing, de novo phasing. We used lysozyme for that. I think I'm the only person who managed to get into science with a lysozyme structure in the last 4 years.
Everybody does.
Yeah. And or in nature actually, and that diffracts really well. 1.6 angstrom, 1.9 angstrom resolution. Myoglobin, we now have 1.5 angstrom resolution for the new data. And for bacteriorhodopsin, we had about 1.8, 1.9 angstrom resolution. Of course, what resolution really is a bit of a religious thing. I like I over sigma to be above 1 at least. Yeah.
And the third question, you are getting, say, a Bragg diffraction, but I'm sure you are also getting lots of diffuse scattering. What do you do with diffuse scattering? Do you interpret diffuse scattering in any way?
I do not, but Henry Chapman's department at CFEL in Hamburg, they have said, okay, well, what you're doing with your Bragg diffraction is that you are sampling the continuous transform of your structure with a Dirac comb, right? That's just convolution theorem. And he says, well, okay, well, so all of the diffuse scattering is, however, related to the molecular transform. And he has collected, so Alexander Yefanov has written software for that, and collected this three-dimensional volume of continuous scattering and used that for direct phasing using a shrink wrap algorithm. That was really, really impressive. I am not sure that it is generally applicable because it depends on a lot of things, being able to measure this scattering. With the photosystem crystals that they had from Petra Fromme's group, there was very, very nice diffuse scattering, and they were able to do that. Yeah.
Mm-hmm. Oh, we have already next questions from the audience. It looks like I have stolen a part of Professor Hans Bedwig's question, but he's asking, diffuse scattering is an alternative for studying dynamics. Can you observe and interpret time-dependent diffuse scattering?
I see no reason why not. Yeah. I have never done it, and I am not aware of anybody who has done it. But I don't see any reason why it shouldn't be possible.
Paulina?
Wojciech Wolf is asking, as I understand, the first LAWA experiment were made by Eric Moffat almost 30 years ago. He has shown the avenue which is taken by carbon oxide to enter the active site. How you determine that what you see is not affected by diffusion of carbon oxide molecule within the protein?
Well, we hope to see the diffusion. That is the goal. Yeah. So we see this really, really fast motion of the CO into its binding pocket, and it is relatively stable there. Also because we don't measure for time scales long enough to see that disappear. This is, however, an enormous problem for other experiments that we're doing with hemoglobin. With hemoglobin, you have 4 myoglobins in a molecule which have different affinities. And there we measure on timescales microseconds where part of the CO simply binds back. It's this geminate recombination. And there is a huge problem because now I have 4 different occupancies. And to be perfectly honest, I don't know yet how to deal with it. Yeah, we have the data, but yeah, no, you're right. That's a huge problem.
So it's like modeling multiple conformation at once, right?
Yeah. Which protein crystallography is notoriously bad at. we have a really, really bad observation to parameter ratio.
Uli Englert, thank you for the talk. In part 1, you mentioned multiphoton effects. How about the opposite? What fraction of possible reaction centers do you trigger with the visible light lasers? Do you see the fraction pattern overlay of photoreacted and unreacted molecules?
Yeah, we do. In that first myoglobin experiment, we had an excited fraction that was so large that we could basically treat it as 100% excited state. But that was, like I said, it was in the multiphoton regime, and now that we're in the one photon or less regime, we necessarily get less than 100% excitation. And the way we deal with that is, difference maps are incredibly sensitive, but to be able to refine it, we use a trick by Ulrich Koenig in 2000, where you extrapolate the differences to 100% occupancy. And this also increases the error bars on the data enormously. The last myoglobin data that I showed, they have about 15% occupancy, 15 to 30% occupancy, and you have to subtract the unexcited, the untriggered part of the data. And you can do that. You should just be aware that it increases your error bars enormously, and use the data accordingly. There are many things that go into this. There is the quantum yield of the system, but there is also simply the alignment of the transition dipoles of your chromophore with the polarization of your laser. We use circularly polarized lights because of this. For another project I haven't talked about here, actually calculated, okay, you have circularly polarized light. I know, of course, of every crystal, I know the orientation matrix. So I know the position, the orientation of all of those dipoles. And then I calculated what the maximum fraction was that I could excite. I was not very high. Yeah? So that's also something that goes into that.
So with such a low occupancy factors, you are at the point that you can make a mistake and interpret your like bonding densities or lone pair densities of not excited molecules with the excited part.
Yeah, so what I typically do is I do this extrapolation, and I look at something that I know is really going to change. Like for instance, the CO is going to move from A to B, or from the ground state to the beat state actually. And I calculate maps for various occupancies, and I use the highest occupancy where I do not yet see the ground state coming back. And that is one way of doing it. There are other ways. Jacques-Philippe Gaultier, Elke de Zitter in his group, she has just written a program. I think it's just accepted that does this automatically for you. It's a very useful tool. But so the dirty little secret of protein crystallography is it only works because there are only 20 amino acids and we know what they look like.
Yes, Professor Hans-Bert Birgi is writing his questions, but before we get it, I have the impression that many of us, especially in the field of quantum crystallography, would love to be more involved in this kind of processing and interpretation and refinement of this kind of data. But you have shown in your acknowledgement how big and strong and powerful and numerous groups have to be in order to somehow get a chance to perform this kind of experiments. Can you be a little bit more specific about the procedure, about the way people are getting access to free electron lasers?
Well, it used to be actually a little bit insidious. Yeah, I guess we had the first successful experiment, so guess who got the second beam time? Yeah. Luckily, the facilities, for instance, LCLS, they are offering screening beam time. So people who have a sample and would like to see how it behaves in the free electron laser beam and whether it is at all useful to apply for beam time, they can go there and they get a few hours of beam time, and either the facility or an experienced group or both will help them. But you don't necessarily need to if you want to work on data processing software and just want to have a look at these densities. Felipe Maya has set up a database, CXIDB, and we have put a lot of data sets there that you can simply download, and you can do anything you want with it, process it again, refine it again. Yeah, maybe I made a mistake.
Okay, thank you very much.
Sure.
There is a question from Hans-Bert Birgi. You showed the oscillations with similar frequencies. Do you know whether they might belong to the same or to different normal modes?
Yeah, I don't know how good our frequency resolution is. I'm guessing it's probably not very impressive. What we are doing is we work with quantum chemists to try to assign these. Yeah, but it's not very easy. But I really don't know whether they belong to the same or to different normal. To be perfectly honest, in a coupled system, I am not sure whether you can say that they really are different. I don't know where that begins and ends.
Okay, thank you very much. Is the last chance to ask the final questions or comments? Yes, I do not see more questions nor comments, and no anybody writing them. Let us thank Thomas and Christian for their excellent lectures. And of course, thank you very much for your participation.